Hello students. So this is our second video in this chapter. So in last lecture we looked at first order transitions, first order or phase transitions. Here now we are going to talk about the second order phase transitions. So what we will basically compare the first order and second order and then discuss how it is different from first order. So there is a classification of these phase transitions, like how do we decide which phase transition is first order and which one is second order. So the classification is given by Hahn first, and what he tells that the order of lowest derivative of the Gibbs enthalpy, that is free energy G, showing a discontinuity upon crossing the coexistence curve, is the order of phase transition. So basically, as we looked at in first order transition, that the first derivatives, which is nothing but the entropy and the specific volume, they were showing the discontinuities when we go from phase 1 to phase 2, that is when we cross that coexistence curve. Coexistence stands for like phase 1 and phase 2 are existing at the same time. That's why we are calling them coexistent. We are calling that curve as coexistence curve. So whenever we cross that coexistence curve, there is a discontinuity in the derivatives of the Gibbs free energy. So whether that discontinuity appears in first order derivatives, then we say that it is a first order transition. Okay, and if that occurs in the second order derivatives, then we say that it is a second order phase transition. So of course, when the second order derivatives are discontinuous, first order derivatives are continuous. Okay, so in this transition, the first order derivatives will be continuous. That means the Gibbs free energy will change continuously. The first order derivatives of the G with respect to T is your entropy, and with respect to P is your volume. So volume and entropy will also change continuously. Okay, which was discontinuous in case of first order phase transitions. So second order phase transition will be relatively continuous phase transition as compared with the first order transition, because here the second order derivatives are discontinuous, first order derivatives are continuous. That is, internal energy and specific volume will change continuously during the phase transition. But the symmetry can change discontinuously. So here the symmetry will be important. We know, like when this kind of phase transitions will appear in something like when the ferromagnetic material becomes paramagnetic material at the Curie temperature, and that kind of transition. So there the state of the system does not change. That means it still remains, the ion in ferromagnetic is same as the state of ion in ferromagnetic, that is your solid state, and the paramagnetic, both are solid states. But since the arrangement of atoms or molecules in the material changes, that means the symmetry changes. Okay, symmetry, you might have studied that in your crystallography units or the solid state physics course. So we will just quickly go through a couple of examples on what happens in this material. So one of the example is this barium titanate. So in BaTiO3, so you have the bariums mostly at the vertices, and then we have oxygen at the center of the face of the cube. So this is a cubic lattice, BaTiO3, and this is just shown a front view of that unit cell. So you have this corners as barium, and then this oxygens, although it appears that it is in the middle of two bariums at the edge, it is actually at the center of this particular phase. Okay, so if you look at this particular phase, something like this, then this oxygen will be at the center here. Okay, similarly at the other points. Okay, This one is also at the face, this one is also at the face, this one is also at the face, and this is also at the face, and there will be one more behind this, exactly behind it. And at the center of the unit cell you have titanium. Getting it? So you have you can think like it is a combination of simple cubic barium plus face centered oxygens and body centered titanium. Okay, so that kind of unit cell we have. Now what happens, this is at high temperature, and when we decrease the temperature of this barium titanate, what happens is barium remains where it is, but this Ti and O, they shift. Okay, they move relative to these barium atoms along the edge of the cube. Okay, and in doing that, you know, this oxygen might go slightly outside and this oxygen will come inside, this oxygen same thing, and then this titanium will move from its central position. And when we do that, basically there will be transitions between ferroelectric and non-ferroelectric material. So this is barium titanate is very popular material for its known for its piezoelectricity. So that is how it basically also generates the piezoelectricity. You can understand when you press the when you apply the stress, there will be change in the distances of this titanium and oxygen, and therefore the central symmetry which balances the charge will basically be disturbed, and therefore this will become charged. This material will become charged, or the part it will be charged on at the edges. So that's how it will develop the charge, and that's why it is piezoelectric material as well. So you can see that the symmetry will be disturbed because of the movement of titanium and oxygen. When it is a cubic, it will have different symmetry than that of after the disturbance or the distortion. So similar, another system we look at is the brass. Okay, particularly the beta brass. So in beta brass, basically you will have a zinc atom at the center, and it is again a cubic lattice, zinc atom at the center and copper at the edges. So you can think like that the central position is always occupied by zinc and the edges are occupied by copper. So central is, it's like different position because it is only occupied by zinc. You cannot have copper there, so it requires different energy. It requires to have different energy or different property, just like for zinc we have. Then only it can occupy that particular position. We call them like that the vertices or the edges where the copper is not same, or the points edges of the or the vertices of the cube are not same as the center of the cube. That is why you cannot occupy or the copper cannot occupy the center. So there is something different between the central lattice point and the vertices lattice point. So that's why we call them unequivalent. So these 2 points are unequivalent. The vertices and the center of the unit cell are unequivalent points because they are not equivalent. If they were equivalent, you might see some copper there, some copper at the center and some zinc atoms at the edges of the cube. So therefore they are unequivalent at that temperature. So when we heat this particular material, what happens is the units, the lattice becomes, or the crystal becomes disordered. So because you know, when we heat, the atoms get energy, they vibrate, they try to move away from their equilibrium positions, and in doing that there is a possibility that this copper now can occupy zinc's position, that is the center of the unit cell, and zinc can also occupy the vertices positions. So that in that way, now because when we add the thermal energy, because of that thermal energy, the distortion happens, and distortion makes the central lattice point and the vertices lattice points equivalent. So now they are like similar points. So so what happens is some of the unit cells will have copper at the center and zinc at the corners, or some copper at some zinc atoms occupy the vertices, and it will might be a mixed kind of system. So again, the symmetry of the system will change now. So here the system is symmetry is changed because of the ordering of the crystal, and in the previous example of barium titanate, the symmetry was changed because of the displacement of the atoms. Alright, so these are the couple of examples of second order phase transitions. In both cases, the material remains in solid state. It does not change this solid state. It does not go into like solid to liquid, but it has undergone the phase transition. Okay, so phase does not always mean change of state. Phase transition does not always mean the change of state. Alright, so let's look at the mathematics involved behind this. So as usual, we have this quantity G equal to G1 minus G2, that is the difference between the free energy, gives free energy of phase 1 and phase 2, that is called the small g. And G will be, of course, because G1 and G2 both are function of pressure and temperatures, so G will also be function of pressure and temperatures. And what we are going to do, or what we need at equilibrium, that the G should be equal to 0. That means G1 should be equal to G2. Alright, again, if we change the temperature by dt and the pressure by dp, then we expect that still the system should remain in the equilibrium. If you remember that phase diagram where the pressure is on y-axis and temperature on x-axis, so if we change the pressure by dt and p by dp, and if we still on the phase equilibrium curve, then we will have equilibrium at that pressure, new pressure p plus dp, and temperature t plus dt. So if we are in equilibrium, that means that particular value of G at that point, at that pressure and temperature, will also be 0. So now we can express this by using again Taylor series expansion. So that will be two variable Taylor series expansion. So you have G of Pt at previous value of pressure and temperature, and this is the new value of G at new pressure and new temperature. So of course this one we have seen for the first order phase transition, and then there will be second order terms also, and then we will have higher order terms, and all together they should be equal to 0. So now we will of course terminate our Taylor series till second order in this particular second order phase transition case. So but here the ΔG and ΔP might have some finite value. So let's say they have some finite value, this particular first order derivative of small g with respect to p and small g with respect to t. Let's say they have some finite value, but the summation of these two, with you have dp multiplied and dt multiplied, that is equal to 0. So that means this. So these are the special cases. Okay, so this is one of the special case, that when this bracket is equal to 0. So if that is the case, then this gives us the Clausius-Clapeyron equation. You know, that is what we have done in first order transition case, and that gives you the Clausius-Clapeyron equation. And additionally here, if we have so here it is the together, so this whole bracket is equal to 0. That means this need not to be 0 and this need not to be 0, but their addition might become equal to 0. Let's say we have a case where they individually are 0, that is the first order derivative ΔG by ΔP is equal to 0 and ΔG by ΔT is also equal to 0. Then if this is 0, this is 0, then we have to consider the second order term. It is possible that we have this equal to whole bracket as equal to 0, but if we have individually first order derivative 0, second order derivative 0, then we have to think about the second order derivative. So in that case we have to express this first order derivative in terms of second order. So ΔG by ΔP, we can write it as the second order derivative of G with respect to P square times dP, and then second order derivative of G with respect to T and again P, then multiplied by dt. So this will give you the first order derivative of G with respect to P. Okay, because we have this dP multiplied, because G is a function of P and T, therefore we are writing it like this. Okay, similarly we can also write double G by double T in terms of their second order derivatives. Okay, so with this, and they should be equal to 0, because we are saying that first order derivatives of G and T are individually 0. Okay, so if that is the case, then we can add them together. Okay, we can add them together, and then we will get this particular term. Okay, we will get this particular bracket when we add them without half, which corresponds to the phase transition of the second order. So when we all the second order derivatives equal to 0, then we will have second order phase transitions case. So if we if the following equalities hold for an arbitrary value of, so this basically if are valid for the arbitrary values of P and T, that is dP and dt, may be positive or negative, then we have this following conditions. If you remember, I have given you this exercise for to prove that if this is true, this is like your a plus b square, and if a plus b square and there is this dP and dt multiplied. So if that is the case, then if that is the case, then whether this particular quantity is greater than 0, or we have to show actually whether this particular quantity is equal to 0. So basically the second order derivatives should be greater than 0 if we can write something like this. Okay, so I hope you might have worked out that exercise. Alright, so when we have this kind of inequalities, for example, we look at this particular case. So here the second order derivative of small g is with respect to temperature is greater than 0. So if we substitute now that small g is nothing but g1 minus g2, and then take them on the other side, so it is greater than 0, so of course it is not equal. So this double g1 here, double 2 by g1 by double t square, that is this, cannot be equal to double second order derivative of g2 with respect to temperature. Okay, because this is not equality, this is inequality. So this term is greater, so of course this two will not be equal to each other, will not be equal. Similarly, the derivative, second order derivative of small g with respect to p will lead us to the second order derivative of g1 with respect to p and g2 with respect to p being not equal. Okay, so we can tell this easily as if we know how to show this. So we don't have to worry about in algebra you might have done, or you can take some simple example and then try to prove that these things are true for arbitrary values of dP and dt. So if we have now we have these derivatives with respect to t, second order derivatives of g's with respect to t and p. Now we can use that the definition of specific volume and entropy. So if you remember, this one we have defined in first order transition case, and this is also defined for the first order transition case. So these are the first order derivatives of Gibbs free energy, therefore this is entropy and this is volume. So if we differentiate that again with respect to, let's say, temperature, then we will get this double g by double t was s, and then another derivative of s, so therefore it is minus double t by double s by double t. Getting it? So similarly, and double s by double t is nothing but double s is what, basically the entropy, and if you multiply the entropy with temperature you will get the internal energy, and when you differentiate internal energy with temperature you get the specific heat, therefore this is Cp and divided by T. Similarly, you can have the derivative of g with respect to p square, second order derivative of g with respect to p, that is pressure, and that will give you, first order derivative will give you sigma, the specific volume, and therefore again one more derivative of specific volume with respect to p, so that is your this, so minus double v by double p. Alright, And we can also express this second order derivative with respect to p and t as this dabba g by dabba p, then take the derivative of that with respect to t. So dabba g by dabba t is volume, and therefore dabba by dabba t of that gives you this dabba v by dabba t. Okay, so we have now expressed all these derivatives in terms of the measure in terms of the thermodynamic quantities like entropy and the specific volume and their derivatives. So now if we substitute all this back to your equation, this equation x, we will get, there are two equations, we will get two terms, and then we can write it as dp by dt. So dp by dt is nothing but the slope of the phase equilibrium curve. So that is what we have done in our first order transition case also. So this gives us the equilibrium curve, okay, equation for the equilibrium curve, and then tells us what are the quantities on which it will depend, and if they are discontinuous, then we can talk about, just like entropy and specific volume, in Clausius-Clapeyron equation, dp by dt equal to that delta S by delta V. That is what we had got. So similarly we will try to get here also. So if we just rearrange this, we will get this particular term, and then ultimately we will write it like this. We have done it only for first case. Second case you can do it, and so dp by dt comes out to be dabba delta S is S2 minus S1 with respect to P, and dabba delta V with respect to P. So it's the ratio of the change in entropies, derivative of change in entropies with respect to pressure, and change in volume, specific volume with respect to pressure. And another case gives you similar but with respect to temperature. Okay, so let me just show you the plots also, how that will look like. So at the second order phase transition, so thermodynamic potentials like the Gibbs free energy are continuous functions, so there is no discontinuity. Okay, whereas their first order derivatives are also continuous, that is dabba g by dabba p, that is nothing but your specific volume. So you can see that it is also continuous. There is slight change, but it's not, you cannot say that it is discontinuous. Okay, then we have first order derivative of g with respect to temperature, that gives you the entropy. Okay, so this is entropy, and that is also continuous. Okay, the heat capacity, again here there will be discontinuity, because heat capacity is the derivative of entropy. Okay, so it is dabba S by dabba T with this and temperature multiplied to it, so that becomes discontinuous. Okay, because it is second order derivative. You can see if you take this becomes like linear function at the transition point. This behaves like a line, and if you take the this becomes almost constant at the equilibrium, and if we take the derivative of that will give you the discontinuity. Okay, so again Cp basically is the heat required to raise the temperature, so that is different for phase 1 and phase 2. So as these are our phase transition equations, second order phase transition equations, just like your Clausius-Clapeyron equations in case of first order transition. Alright, so with this we finish the second order phase transitions. Then we will look at some different theories about these phase transitions. So this is just basic models of phase transition. So you remember first order phase transition, first derivatives of the Gibbs free energy are discontinuous. Second order phase transitions, second order derivatives of the Gibbs free energies are discontinuous. Okay. Alright, so we'll stop it here. Next lecture we'll look at the indices, and then Landau theory of phase transition, and so on. Alright, so I will stop it here, and then we will talk about the next slides maybe in a couple of days. I will post that. So take care, don't go outside, just be inside, be safe. Alright, bye.